Good afternoon. Today we're going to be talking about section 4.2, the mean value theorem. And this is a very theory-heavy lecture. There's not a whole lot of applications to this that I can show you, no like real-world problems like we saw in section 311. So you're just going to have to bear with me. If you're a math major, maybe you'll find this really compelling and interesting. And if you're not a math major, well, try and absorb how all of the machinery works and see if you can't remember it, because it's going to be kind of useful for the homeworks and the exams. So we start off with a theorem, and this one is called Rolle's theorem. Let a function f be continuous on a closed interval ab and differentiable on an open interval ab with f of a equals f of b. Then there is at least one point c in a to b such that f prime of c equals 0. So what does this look like? Let's start with an example. Given f of x equals x cubed minus 7x squared plus 10x, first find an interval I on which Rolle's theorem applies, and then find all the points c within I at which f prime of c equals 0. So let's get started. So part A, find an interval on which Rolle's theorem applies. Rolle's theorem requires that we have continuity and differentiability on our interval. But because f of x is a polynomial, it's continuous and differentiable everywhere. So let me write that down. So all we need to do is find a and b such that f of a equals f of b. And we do that by first factoring our polynomial. So f of x can also be written as follows. We choose our interval I to be the closed interval 0 to 5 because f of 0 equals 0 and f of 5 equals 0. So we have a and b, 0 and 5, such that f of a equals f of b. And it's easiest to just pick where the zeros are. And luckily this factors pretty nicely. So we found an interval on which Rolle's theorem applies. Excellent job. Next, we're interested in finding all the points within our interval at which f prime of c equals 0. So we're looking for critical points. So the first thing we do is differentiate. F prime of x is equal to 3x squared minus 14x plus 10. Then we set f prime of x equal to 0 and solve for x using the quadratic formula. And we get that x equals 7 plus or minus the square root of 19 all over 3, or x equals 0.88 and 3.79. So I'm going to take this one step. So we found the zeros, we found the critical points, and we found an interval on which we have critical points. I'm going to take it one step further, and I'm going to say, can I draw my original function, just given information based on the derivative? And the answer is yes. So the first thing I want to do is remember when we factored our function, we got f of x equals x times x minus 2 times x minus 5. we know that those are all the places where we have zeros. So if I've got a 0 here, I'm going to change that to red. I've got a 0 here, I've got a 0 here, and I've got a 0 here. And I know that I've got an x cubed, just 1 times x cubed, so I should have something that points up this way and points down this way. So now I'm ready to draw my function. If I know that we have to be pointing up as we exit 5, then that goes like that, and we have to be pointing down as we exit x equals 0, then we should probably have something that goes a little like this between x equals 0 and x equals 2, and a little like that between x equals 2 and x equals 5. And in fact, we know that we have zeros, or we know that we have points where the tangent line equals 0 at 0.88. So we have a local maximum right there, and we have a local minimum at 3.79. So that's about right here. So now I've drawn my function. Well, how do I know that this is correct? And the answer is, well, we Google it. So I went ahead and Googled it, and we can see we've got zeros at x equals 0, x equals 2, and x equals 5. Because we've got a cubed root function, as we exit 5, we're pointing up, and as we approach 0, we're pointing down. I've got a local maximum, just like I predicted, at 0.88, and I've got a local minimum, just like I predicted, at 3.79. So we can use Rolle's theorem to find critical points, and with our critical points and our zeros, we can draw our function, which is pretty powerful and pretty cool. You don't need a graphing instrument to be able to draw functions because we have calculus, and I think that that's just one of the coolest things ever. So now that we've talked about Rolle's theorem, let's get into the entire point of this chapter, which is the mean value theorem. Let f, a function, be continuous on a closed interval a to b and differentiable on an open interval a to b. Then there is at least one point c within a to b such that f of b minus f of a over b minus a is equal to f prime of c. So let's go ahead and jump right into an example to try and process what this is asking us to do. So let f of x equal 2x cubed minus 3x plus 1. Determine whether the function satisfies the conditions of the mean value theorem on this interval, -2 to 2, and then find the points guaranteed to exist by the theorem. So let's jump in to part A. In order to satisfy the mean value theorem, f must be continuous on a to b, and f must be differentiable on the open interval a to b. Now, we're working with a polynomial, so we know that it's continuous everywhere and it's differentiable everywhere. So check, check, we satisfy all of the conditions of the mean value theorem, we can proceed. So now we're interested in finding the points guaranteed to exist by the mean value theorem. So we start with f of b minus f of a equals, or b minus a equals f prime of c. When we plug everything in, we get f of 2 minus f of -2 all over 2 minus -2, which is the same as 11 minus 9 minus -9 over 4, which is the same as 5, because we end up with 20 divided by 4. So our goal is to find points within -2 to 2 at which f prime of x equals 5. So the first thing we're going to do is differentiate. So f prime of x equals 6x squared minus 3. And our next step, which is different from what we did using Rolle's theorem, is setting this equal to 5 and then solving for x. So x squared is equal to 8 over 6. I just did some quick maths. or x equals plus or minus 1.15. And this just tells us that at positive 1.15 and negative 1.15, we have the slope equal to positive 5. So at both 1.15 and negative 1.15, we've got an m tangent equals 5. The slope of our function is equal to 5. And that's it for me today.